Next, we're going to look at the theorems that show us how to find powers of complex numbers and roots of complex numbers. So let's start with powers. And because we already know how to multiply complex numbers, this is really easy to show that this formula will work. Because when we find powers, so we're talking about whole number powers like z squared, z cubed, etc. If we have z in polar form, then we're taking z times z, of course. So we can just use our formula for multiplication to show that this would be r times the cosine of theta plus I times the sine of theta plus theta. So r squared cosine 2 theta plus I sine 2 theta. And then with the next power, z cubed, we would take the result for z squared and multiply it times z. So we'd get r times r squared is r cubed cosine of theta plus 2 theta. And of course that's 3 theta. I'll just write 3 theta in the second argument here. So this is 3 theta. Just write, instead of rewriting it, I'll just write it like that. And then z to the fourth, we'd get r times r to the fourth. And then 3 theta plus theta would be 4 theta, etc. So we can just generalize as z to the n. Notice this power will match this power, right? Will be z to the, r to the n. Times the cosine of n theta plus I times the sine of n theta. So notice the power here matches the coefficient on theta. This saves us a ton of work. So let's do an example. If I want to take this to the 10th power in rectangular form, I have to multiply the first two, FOIL, reduce I squared, then take that answer times z again, do the same thing, get an answer, in a plus bi form, etc. That's a lot of work. If we convert this to polar form, this is really easy. So in polar form, z equals, first we find r, square root of 1 plus, negative 1 squared is 1, square root of 3 squared is 3, so square root of 4, which is 2, and then theta, so would be negative 1 square root of 3. So in quadrant 2, and the tangent of theta is negative square root of 3, so which implies theta is 2 pi over 3. So this will equal 2 times the cosine of 2 pi over 3 plus I times the sine of 2 pi over 3. So z to the 10th will be 2 to the 10th cosine, and so we'll take 2 pi over 3 times 10, 10 times 2 pi over 3, plus I sine 10 times 2 pi over 3 again. So 2 to the 10th, and this would be 20 pi over 3, and 20 thirds is 6 2/3. So we'd have 3 complete rotations. So this is actually coterminal to 2 pi over 3, the extra 2/3, right? We'd go around 1, 2, 3 times, and then 2/3 of the way. So I'm just going to change this to 2 pi over 3. Oops, forgot my I. And we could leave it like that, but let's see what that would be in rectangular form. So 2 to the 10th is 1024. And then cosine of 2 pi over 3 excuse me, is negative 1/2. No, yes, negative, sorry. Plus sine of 2 pi over 3 is positive square root of 3 over 2. So 2 goes into there 512 times, negative 512 plus 512 square root of 3i. I'll put the I here so it doesn't look like it's under the radical. Okay, so it depends on how you want your answer. Do you want it in rectangular form or do you want it in, what did I say? I think I said the wrong thing. Do you want it in trigonometric form / polar form, or do you want it in rectangular form? But you can see either way, even if you have to go to rectangular form, this is pretty short amount of work for raising a number with 2 terms to the 10th power. So this theorem is really nice if we need to take powers of complex numbers. Let's do one more, let's make sure we understand. So 1 minus I would be in quadrant 4, right? And the radius would be the square root of 1 plus 1, which is the square root of 2. So square root of 2 cosine of, let's do this one in degrees. You know, you can use degrees or radians. I usually use radians, but let's do it in degrees just so we get used to both. As I say, quadrant 4, right? So over 1 down 1. So this would be 315 degrees plus I sine 315 degrees. So one minus I to the 4th power will be the square root of 2 to the 4th power times cosine. So 315 times 4 is 1260 degrees plus I sine of 1260 degrees. So again, this is 4 times 315 degrees. But this would also be 7 pi over 4. So you could, and times 4, that would make this a 7 pi. And so for me, that would actually be nicer in this situation, because I know 7 pi is going to end up on the unit circle at the point -1, 0. Okay, so square root of 2 to the 4th will be 2 times 2, which is 4. Cosine of 7 pi is -1. Sine of 7 pi is 0. And so this is equal to -4 if we convert back to rectangular form. So really quick and easy to do powers. Now we're going to look at complex roots, and we're not going to derive this theorem, but we're just going to state it. It's a little more involved to derive, but notice if it's this form is similar. Instead of raising to the nth power, we take the nth root, and instead of multiplying by n, we divide by n. However, we have to do this little extra thing here. What does this mean? So for if this is like, say, a 4th root, wait, you're going to find all 4 roots. Okay, this is what this is saying. So we have this complex number, and whatever n is, so if you're doing a 4th root, then there's going to be 4 distinct 4th roots. We're going to call the first one z sub 0, the second one z sub 1, third z sub 2, and then if it's a 4th root, the last one is z sub 3. So this is always subscripted with starting at 0, so the last subscript is 1 less than n. Okay, and we're going to call the last one in general k here. So you're going to take, for the first root, this k is 0, so it would just be theta divided by n. For the second root, you're going to add theta, so theta is the argument up here, right, to 2 pi, and then divide by n, or if you're using degrees, add 360 and then divide by n. For the third root, now k is 2, so you're going to take theta plus 4 pi divided by n, or theta 360 times 2 is 720 divided by n, and etc. When we do an example, that will become more clear. And of course, these arguments are the same in both terms. So you're going to find all of the roots. There's going to have more than one answer. Unlike the powers, right? There's only one answer. There's one power. One other thing I should point out. Oh, it's on the other back of the page. These are both called Dumas theorem. This one is called the Dumas theorem for powers. The other is for roots. Right? Complex roots. So here is an example that will illustrate what we're doing here. We're going to do actually four examples. So when we take a number, and this is a number, of course, you're familiar with, it's just 16. I'm going to pause my video. I'm sorry, my dog is acting up.